In this presentation, we'll model mechanical systems with both elastic and damping elements. And we'll start off with the classical mass spring damper system. And you'll see this system a lot in various engineering applications. The reason why is because it's the simplest system that contains all three elements of inertia, elasticity, and damping. So here's the system we'll treat. It's a mass sliding on a tabletop with a spring and a damper and an applied force, F sub I. We measure the displacement of the mass by x, which will be to the right for the positive direction. The positive direction for F sub I will also be to the right. The spring constant is k, and the damping constant is denoted c. We'll make a free body diagram of this system in order to write the equations of motion. Three forces are acting on our mass in our free body diagram. There's the applied input force F sub I, and there's a force from the spring F sub S, and one from the damper F sub D. I'm choosing to the right as the positive direction for all three of these forces. And I'm also choosing to the right as the positive direction for displacement x. With this free body diagram, I can write the following equation of motion. mx double dot equals fs plus fd plus fi. Now we need to find the relationships between the spring force and damping force and displacement and velocity. For the spring force, well, we've encountered this before. F sub s equals minus kx, because if there's a positive displacement to the right, then the spring force will be negative. For the damping force, the relation is F sub d equals minus cx dot, because if the mass is moving rightward, then x dot is positive, and the damper will try to prevent this motion, so F sub d will be negative. Substituting these relationships for F sub s and F sub d into our equation for mx double dot, we find the following equation of motion. mx double dot equals minus kx minus cx dot plus F sub I. We bring the x terms over to the left-hand side, and we get mx double dot plus cx dot plus kx equals F sub I. We Laplace transform this expression, and we'll find ms squared plus cs plus k times x of s equals fi of s. We then divide through by ms squared plus cs plus k, and we find the following relationship between input f sub I and output x of s. This relationship is governed by the transfer function, which we label h of s, and which is 1 over ms squared plus cs plus k. This transfer function we'll see many times in this class, because the classical mass spring damper system is so common in engineering. So you should be very familiar with the transfer function 1 over ms squared plus cs plus k by the end of this course. Transfer function h of s has no zeros, no roots of its numerator polynomial, and it has two poles, that is, two roots of its denominator polynomial. These poles are easy to find. They're just the roots of ms squared plus cs plus k, and that's a quadratic, so we can find these roots by applying the quadratic formula. The quadratic formula will show that as long as m, c, and k are positive, these poles will be in the left half plane. Since physically, inertia is always positive, damping is always positive, and stiffness is always positive, we know these poles will be in the left half plane, and so the system will be Bibo stable and also asymptotically stable. There are two possible ways of distributing our two poles in the left half of the complex plane. In the first case, the two poles are complex conjugates, and in the second case, they are both on the real axis. The impulse response will differ depending upon which of these cases holds. If the poles are complex conjugates, then the response to an impulse will be an oscillatory response, a dampening sinusoid. If the poles are real, then the response will not oscillate and will be what is called an overdamped response. We'll now examine a system with two masses and a damper in between them. Mass M1 is tied to a wall by spring K. Between M1 and M2 is the damper, and we have an input force acting on M2. Now, this problem can be a bit tricky compared to the single mass problem. The important thing to remember is the damper acts to oppose the relative velocity between the two inertial elements. That is, it opposes lengthening and contracting. It doesn't particularly care what the distance between the two masses is, unlike a spring, but it cares about the change in the distance between the two masses. So, if the two masses are moving relatively closer together, the damper will act to oppose this motion. That is, it'll push the two masses apart. And if the two masses are acting to increase their distance between each other, then the damper will oppose this. It will pull them together. One important thing to remember about a case where we have a damper between two inertial elements is the damper may act to actually transfer energy from one element to another. So while dampers dissipate energy of the entire system, they may transfer energy from one part of a system to another. Let's draw free-body diagrams for the two masses in this system. So for mass 1, I'll have two forces acting upon it. I'll have a force from the spring and a force from the damper. The spring force I label F sub S, and the damper force I label F sub D1. The 1 subscript indicates this is the damper force acting on mass 1. Note that I've drawn both forces to the right. I could have drawn them either way, but I just chose to draw them to the right, so that's the positive direction for these forces. For mass M2, there are two forces acting on it as well. There's the input force Fi, and there's a force from the damper, which I label FD2. I've chosen to draw both of these to the right as well. That just indicates the positive direction for these two forces. So, given these two free body diagrams, I can then write my equations of motion. I'll have m1 x1 double dot equals fs plus fd1, and m2 x2 double dot equals fd2 plus fi. Now we need to determine how these forces, Fs, Fd1, and Fd2, are related to the motion of the two masses. For the spring, this is quite easy. We've tackled problems like this before. The spring force will act to oppose the positive displacement of x1 by producing a force in the leftward direction. That tells us that Fs must be equal to minus kx1. Now the harder problem. How are the damping forces related to the velocities of mass 1 and mass 2? We'll begin by looking at Fd1, the damping force acting on mass 1. How is it related to the relative velocity of the two masses, that is x2 dot minus x1 dot? Let's think carefully about this. There are two possible ways in which Fd1 is related to the relative velocity x2 dot minus x1 dot. One is Fd1 equals c times x2 dot minus x1 dot, and the other is Fd1 equals minus c times x2 dot minus x1 dot. Which of these two possibilities is correct? To answer the question, we'll perform a thought experiment. Let's suppose x2 dot equals 0, that is, mass 2 is still, and that x1 dot is positive. so mass 1 is moving to the right. What this means is the damper must be contracting in this case. So the force acting on M1 in this case should oppose the motion. That is, FD1 should be toward the left. So when x2 dot is equal to 0 and x1 dot is positive, we know that FD1 should be to the left. Now, which of our two possibilities would agree with this? Would it be FD1 equals C times x2 dot minus x1 dot, or would it be FD1 equals minus C times x2 dot minus x1 dot? Now recall for our thought experiment that we supposed that x1 dot was greater than 0 and x2 dot was equal to 0. So x2 dot minus x1 dot should be negative. Now we look at our two possibilities for FD1. FD1 equals C times x2 dot minus x1 dot, or FD1 equals minus C times x2 dot minus x1 dot. In our thought experiment, x21 dot minus x1 dot is negative. So FD1 in the first case, the green box, would be negative, and FD1 in the second case, the blue box, would be positive. Now we know that FD1 should be to the left, and that's the negative direction for FD1 in our Freebody diagram. So that tells us that it's the first case, the green box, FD1 equals C times x2 dot minus x1 dot, which is physically correct. So using our thought experiment, we have figured out what the relationship is between the relative velocity and the damping force on mass 1. And the correct relationship is FD1 equals C times x2 dot minus x1 dot. Using exactly the same kind of logic, we can arrive at the condition for the damper force on mass 2. And it is FD2 equals minus C times x2 dot minus x1 dot. So we have expressions for F sub s, FD1, and FD2. And we can substitute these into our equations of motion. And we'll arrive at the following. M1 x1 double dot equals minus k times x1 plus c times x2 dot minus x1 dot. And M2 x2 double dot equals minus c times x2 dot minus x1 dot plus f sub I. We'll now do a bit of algebra. We'll move the x1 terms in the first equation to the left-hand side, and we'll move the x2 terms in the second equation to the left-hand side. And we'll have m1 x1 double dot plus cx1 dot plus kx1 equals cx2 dot, and m2 x2 double dot plus cx2 dot equals cx1 dot plus f sub I. And we'll Laplace transform these equations and of course assume zero initial conditions because we're trying to find the transfer functions. And that will give m1 s squared plus cs plus k x1 of s equals cs x2 of s. And m2 s squared plus cs times x2 of s equals cs x1 of s plus f sub I of s. We'll suppose that we're interested in the motion of mass m2. That's the one that the force is acting upon. So we'll make our output y of t equal to x2 of t. And of course, when we Laplace transform this expression, we'll find y of s equals x2 of s. So we want to find x2 of s because that's going to be our output. So, toward that goal, let's take the equation of motion for mass number 1, and we'll solve for x1 of s. We'll find x1 of s is equal to cs over m1 s squared plus cs plus k times x2 of s. So this is a relationship between the motion of mass 2 and the motion of mass 1. We'll now plug this into the equation of motion number 2 in order to eliminate the variable x1 of s. That will give us the equation m2 s squared plus cs times x2 of s is equal to cs times the transfer function cs over m1 s squared plus cs plus k times x2 of s plus fi of s. So everything here is in terms of x2 of s and the input fi of s. So we just have to gather together all the x2 of s terms on the left-hand side, do a little bit of algebra, and then we can find the transfer function between the input fi of s and the output x2 of s. So here I'm carrying out this algebra. I gather all the terms on the left-hand side, and then I find a common denominator for the terms. And that gives me, when I multiply things out, a fourth order numerator over a second order denominator multiplied by x2 of s equals fi of s. And so now I'm going to take the thing in the curly brackets and divide both sides by it, bringing it over onto the right-hand side. And that gives me the transfer function between my input fi and my output x2 of s. And I write that as the ratio x2 of s over fi of s is equal to second order numerator divided by fourth order denominator. And I note the fact that my fourth order denominator can be factored as an s times a third order term. So we know that this transfer function has one pole at the origin, and it will have three poles in the left half plane, as long as m1, m2, c, and k are all positive, which they will be. The zeros of this transfer function will also be in the left half plane. They're the roots of m1 s squared plus cs plus k. Now the exact location of the poles and the zeros is determined by m1, m2, c, and k, and we haven't specified those here. For the purposes of illustration, let's just draw where the poles and zeros might possibly be. I'm showing two zeros in the left half of the complex plane, and they are complex conjugates. Then I'm showing three poles in the left half plane. Two are complex conjugates and one is on the real axis. With three poles, we know that one has to be on the real axis. Perhaps all three will be, but we know that one has to be. And finally, I'm showing one pole at the origin. And I know one pole at the origin because I could factor out that s in the denominator of the transfer function. What do these poles tell us about the way the system will respond to an impulsive force acting on mass m2? We have one pole at the origin, and so the characteristic mode associated with this will be a step. And then we have two complex conjugate poles. The characteristic mode associated with these would be a dampening sinusoid. And then we have one pole that's on the real axis. The characteristic mode associated with this pole is an e to the minus at, where the pole is located at minus a. We know the impulse response will have a form that is the sum of these characteristic modes. The unit step in this summation, due to the pole at the origin, indicates that the impulse response will not decay back to zero. Therefore, we know that the system will not be Bibo stable, since the area under the absolute value of h of tau curve is not finite. That's not surprising. We know with a pole at the origin that we cannot expect bounded input, bounded output stability. With the pole at the origin, this system will not have asymptotic stability. That should not be surprising either, because we know if we took mass m2 n were to displace its initial condition so that x2 is positive, that is, mass m2 has been moved to the right, then the damper would not act to return mass m2 back to the origin. There's no force from the damper that responds to the damper having increased length. The damper only responds to a changing value of its length.